Welcome to Chemistry 111. So we're going to continue with our ideal gas law right now. So last class, we were talking about the individual gas laws and how when we put them together, we get PV equals nRT. Pressure times volume equals the moles times the gas constant R times temperature in Kelvin. Doing that, you can relate these four variables with the constant R. And that if you know 3 out of the 4, you can figure out the 4th. Then one last thing we finished up with was talking about how standard temperature and pressure. At standard temperature, which is 0 degrees Celsius, 273 degrees Kelvin, and 1 atmosphere, 1 mole of gas has a volume of 22.4 liters. Right, so compare that to, say, water. 1 mole of water, liquid water, would be 18 milliliters. 18 milliliters. So 0.018 liters. If not smaller, considering the whole changing density. But okay. We're going to start off this class period by looking at some potential applications. So it's all well and good to have PV equals nRT, but what does it mean to actually use it? So this chapter especially, but the last chapter as well, is a chapter filled with equations. We need to recognize what equations to use and how to use them. For the most part, I'm going to write the equation. I'm going to define my variables. I'm going to evaluate the equations so that I'm going to isolate the one unknown. We're going to plug in and we're going to solve. So hypothetically here, 1 mole of argon gas is being stored in a 2-liter container is then heated to 300 degrees Celsius. What is the pressure of this container? Let's first, I'll go to the main screen. So we have our P, our V equals nRT. So let's define what we know. We don't know the pressure. We want to know what is the pressure. Our volume is given as 2 liters. Our moles, 1 mole. Our R is a constant. While I don't give you the units of the pressure, I remember that I really meant to ask for bars, but even if I use the wrong one, I'll show you how big a difference it changes. It's not really that big a difference. T is 300 degrees Celsius. So, with that in mind, we need to turn Celsius into Kelvin. So we add 273. That would give us 573 Kelvin. Let's see. With that in mind, isolate the pressure. So we'll say, to do that, we'll divide both sides by V. So we have P equals nRT over V. So with that in mind, we plug in everything we're given. We have 1 times R times 573 divide by 2. We do this bar liters per mole Kelvin moles cancel, liters cancel, Kelvin cancels. We're left with units of bars. If you do that, if I'm not mistaken, you should get something like 23 some. Let's figure out the exact number. You get 23.8. 23.8 bar. 8.2 if you want to get really technical. Now, hypothetically, say you didn't remember the correct R. What happens if you would have used 0.08206? If you had accidentally switched it up, what answer would you have gotten? 23.51. 23.51. So it is a rounding error at best. It typically it's typically 1% error, if not a little less. Okay. Okay. 1% error. So take that as you will. I won't usually be able to mark that wrong on a test because it's usually within 1% of the accurate score, rounding one way or the other. Now, second problem. The container can safely hold 300 psi of pressure. What temperature in Celsius could it handle before exploding? Hint, and I give you the conversion of psi to bar. So same 1 mole of gas, same 2-liter container. So now we don't know that, but we do know our pressure. 300 psi. 300 psi. Now, we have to convert psi to bar. I give you it's 14.5 for psi in 1 bar. So let's do a quick conversion. So 300, 15.504, get 20.68. 20.68 bar. So that container's going to explode. We've heated it to 300. That's not good. For those of you who have seen Jaws, we've seen what happens when air cylinders explosively decompress. Yeah, they can be dangerous. They can punch through cinder blocks with no problem. You can have your own little mini rocket shooting through the ceiling and then coming down like a bomb. They are incredibly dangerous. So, which is typically why you don't want to drop them. You don't want to allow them to stay in a fire. They are pretty bad. So we are going to isolate the T at this point. So we're going to divide both sides by NR. PV over NR equals our temperature. So 20.68 bar times my 2 liters divided by my 1 mole divided by my R constant, 0.08314 equals temperature in Kelvin. Temperature in Kelvin. So 6 times 2 divided by. So you would get something like 497.5, 497.6 Kelvin. 497.6 Kelvin. To answer the question, we have to turn it back into Celsius by subtracting 273. Your answer would be it can be heated up to 224.5 before it pops. Does that mean, oh, good, we can safely heat it up to 220? I wouldn't do that, but there's a safety regulation usually for a reason. So we're not going to accidentally spill boiling water on it and it's going to pop. But you leave it in a fire. There's a fire in your restaurant and you have compressed air somewhere. Those things can explode. But okay, so that is two problems. Just using PV equals nRT. What I did, remember, I got my equation. I stated everything I know, what variable it is. I did whatever relevant conversions I needed. I isolated the variable, and then I plugged in and solved. Do one more problem, just like that. So this one may be a little bit more realistic, a little bit more annoying though. A 20 cubic foot acetylene tank. So if you ever need a blowtorch, need to weld something, you might be using some acetylene. That's your ethine. But essentially it's carbon, triple bonded carbon. Burns really well, lots of energy density. A 20 cubic foot acetylene tank at a pressure of 225 psi at the room temperature of 25 degrees. How many moles of acetylene could that tank hold at 225 psi? So in this case, we're working with atmospheres. I give you the conversion 14.7. But you could just as easily convert this into bars and then work from there. So this one has a little bit more conversion. So we have a temperature at 25 degrees C. We have our gas constant as 0.08206 ATM liter mole Kelvin. Moles is unknown. Volume is 20 cubic foot, so that's feet cubed. And pressure is 225 psi. So with that in mind, I give you the conversion of cubic feet. I give you the conversion of psi. We'll start by doing that. So there is 14.7 psi per 1 atmosphere. So how many atmospheres of pressure? It's going to be a decent amount, but how many? 225 to 14. 7. That's 15.3. Keep in mind, we typically on a regular day feel 1 atmosphere of pressure. As we go underwater, I think for every 10 feet or something, I think the pressure maybe doubles or something like that. But so it's like this type of pressure, you're definitely scuba diving pretty deep. 20 cubic foot, I say in 1 cubic foot, we have 28.3 liters. So 20 cubic feet is going to be 566 liters. And finally, turning 25 degrees into Kelvin, we have 298 Kelvin. We got all of our units. We're going to isolate our moles, get it by itself. So we have PV over RT equals N. And now we just plug in and solve. So 15.3 times 566 divided by 298, also divided by our R. So we evaluate that, you get, that would be 354 moles. So a good chunk of gas. Good chunk of gas, 354 moles. Now, of course, if you want to store more gas, what would you have to do? You would have to push it up to a higher pressure, because that gas tank is not going to get bigger just because you pumped more gas into there. So you would have a higher pressure. If I put up 300 psi, I would have more moles of gas. But, okay. This is just practical application of ideal gas equation. Just giving you all the variables you need except for the one we're asking for. But pretty straightforward if you got this. Okay. Now, because these gases are treated as ideal, each gas is treated as identical. So that leads to a pretty interesting thing when we mix gases together. So if you remember, you might not, it's been a while, in this early second chapter, we started by talking about this fellow by the name of John Dalton. He had his theory of atoms, in the atomic theory where, atoms are the smallest individual units, and that compounds go together in a certain ratio and all that jazz. But he also did a bunch of work with gases at the same time. So one of the things he found is that the total pressure of a mixture of gases actually turns out to be the sum of the pressure of each individual gas. So if I have two gases in the same quantities, and I know the pressure of one, the total pressure would be the sum of, it'd be essentially doubled. So if I have 1 mole of this gas and 1 mole of that gas, and the 1 mole gave me 1 atmosphere, if I mix them together, 1 plus 1 would give us 2 atmospheres of pressure. But so from this concept, we get the idea of partial pressures. Partial pressure is a pressure of an individual gas within a mixture. When you say, like, well, why are we dealing with individual gases? Well, we're dealing with individual gases every day, whether we want to think about it. Air is not an individual gas. Air is actually a mixture. We have like 75, 78% nitrogen, some odd 20% oxygen, and then we start to get in trace gases like CO2, water, depending on the relative humidity, we get some argon, and we get smaller and smaller quantities of a whole bunch of other gases. So the pressure we are feeling is actually pressure from all these gases summed up to give the total pressure. Now, because the pressure total is just the sum of all of the individual pressures, and we can relate pressure to moles by the ideal gas equation, we can say that the pressure total is related to the mole total of all the gases by what is the temperature and what volume are they filling. So the volume will not change when I'm adding more gases. If I add a bunch more gases to the room I'm in, the total volume will not change if the door is closed. The temperature ideally should not change if the gases are allowed to equilibrate and get at all the same temperature. So the only thing that'll change is the pressure because the moles went up. Okay, so from there we get Dalton's law of partial pressures. That essentially, if we know the partial pressure and we know the total pressure, we can figure out what percentage of the mixture each gas is. That we look at, if I have two gases, each one atmosphere, you would have a total of 2. So 1 over 2, or 1/2, would give me a 0.5, or 50%. 50% of the pressure is made up of gas 1. And so we get a concept called a mole fraction. We're not going to really use this too much. You might use it later on in chemistry, but right now we're not going to use it super much. But essentially, a mole fraction is as it reads. It's what fraction of the total moles is this mole. If I take the total moles and divide by, well, I take the individual moles of one guy and divide by the total moles, you'd get a mole fraction. But basically, if I know the mole fraction, if I know what percentage this gas is, and I multiply by the pressure total, I can get what is the individual pressure. So let's just give an example. I mix 1 mole of hydrogen with 3 moles of helium. So you get a total of 4 moles of gas. 1 out of 4 is 25%, mole fraction of 0.25. 3 out of 4, which is the other guy, is 75%, or 0.75. So meaning, if I had a total pressure of 1 atmosphere, 25% of that would be hydrogen, so 0.25 atmospheres. The other 0.75 being helium. If I instead had 4 bars, 25% of 4 is 1. And the other 3 is made up of helium. So any fraction I could give you, this is 250 torr. 25% of 250 would be how much hydrogen is. And then 75% of 250 would be how much helium is. Doesn't matter the number. It doesn't have to be a perfect number, but we're going to have a relationship. Now, this next problem is a hot mess. It is about one of the hardest ones I could possibly give you here, and I don't think I'm going to give you anything this hard. I'll show some test questions at a later time, and you'll see, he doesn't ask for nearly something as hard. It's more like the situation we asked down there. But right here, let's look at this. So the first thing is just a statement that is important, that will be useful in the question. The second bullet point is the actual question. The pressure of water vapor, which is the vapor pressure, depends only on the water temperature, meaning the amount of water in the air depends on how warm it is. Right now, it's pretty chilly, and so the vapor pressure of water is going to be pretty low. It cannot be very humid if it's really cold out. If the water is really warm, it could be very, very humid, to the point where if you're boiling water, which is 100 degrees C, you're producing 100% vapor pressure, 1 atmosphere worth of vapor pressure. That's 760 torr of vapor pressure. That's 1 atmosphere. So, if 1.5 liters of oxygen was collected under a 35-degree water at a barometric pressure of 755 torr, 1, what is the pressure of oxygen? And 2, how many moles of oxygen does that actually count as? So, with that in mind, we are going to use both the ideal gas equation and the Dalton's law of partial pressure. Basically, this is like the experiments I was doing a couple weeks ago when I was collecting laughing gas. You're essentially producing a gas, you're bubbling it through water and displacing the water in an empty flask so that we can get pure oxygen, or at least nearly pure oxygen. In this case, you'd be getting oxygen and a little bit of water, depending on what the temperature of water is. So, the total pressure of this whole system is 755 torr. And I'm giving you the temperature of water. So question 1, what is the pressure of the gas? Question 1 has to do with what is the pressure of water, and thus what must be the pressure of oxygen. So let's just work that out. So the P total equals our P of O2 plus our P of water. This is collected under an external pressure of 755 torr. Then PO2 plus P water must give us our 755. Now, because this is collected with 35 degrees water, the vapor pressure of water at 35 from this chart was 42.175 torr, meaning the pressure of oxygen is the difference between 755 and 42.175. Which is 712 point, we'll say 83. So PO2 would be 712.8, well, go 825 torr. So that is that. Now the second question says, so how many moles of oxygen is that? So we're going to use the pressure of oxygen, the volume it's trapped under, and the temperature. Forgot the moles. First things first is I need to turn torr into atmospheres. Conveniently, 1 atmosphere is 760 torr. On a test, I would absolutely give you this conversion. But in the meantime, I know this by heart. So 0.9379 ATM. Looking back at the question, it says the volume it's trapped under is what, 1.5 liters. And the temperature is 35 degrees. The 35 degree water is going to make it 35 degree oxygen. So adding 273 brings it to 308 Kelvin. And because I'm using atmospheres, R would be 0.08206 atmosphere liter mole Kelvin. So coming up, PV over RT equals N. Plugging our numbers in, 0.9379 times 1.5 divided by 308 and divided by 8206. So in this particular case, pressure is relatively low. Volume is relatively low. Temperature is reasonable. So how much gas do we have? The moles would be 0.055, let's say 7 moles, or 5566 moles. So with that in mind, once we take care of the Dalton's part, it just becomes an ideal gas equation problem again. It is not necessarily that hard once we get rid of the Dalton's issue. You could have gone about it in a different way. You could have used the total pressure to figure out the total moles of gas. And then using Dalton's, you find out there's 712 torr out of 755. figure out that fraction, then multiply the total moles by that fraction to give you the actual moles. But we'll get the same answer either way. But as I said, that's probably one of the hardest problems given. That I'm taking hard and I'm trying to work it back to simple on the achieve and on the test. So we'll see the worst it can be, and we'll see, oh, it's not nearly as bad. This is a good one that actually a realistic problem. So there's a few other things we can do with the ideal gas equation. One, but this equation requires us to know what the gas is. We can calculate the density of a known gas if we know the molar mass. Or if we know the density, we can calculate its molar mass. How can we do this? To this, we need to remember density is mass over volume. And mass is equal to moles times molar mass. So combining those two concepts together, we get density equals moles times molar mass over volume. Well, isolating moles and volume from the ideal gas equation, you get moles per volume equals pressure over RT. And if we multiply both sides by molar mass, we get that density of a gas equals its pressure times its molar mass over R and the temperature. So with this in mind, what good is this equation? Besides obviously, besides obviously we can find the gas if we know the density. What do we know about hot air? What do we know about hot air? Hot air does what? It rises as opposed to cold air. Rises. So why is that? Well, it's based on this equation right here. If I consider the pressure of two bodies of air, but at different temperatures, if one is at, say, 0 degrees, it's really frigid out, you would be dividing pressure times its molar mass divided by 273. If the other air was, say, hot, we'll just say even just we'll just say 350. Not quite boiling. Well, that's a little bit too hard. Maybe like 320 degrees. You would be dividing by a bigger number. What happens to a fraction when you divide by a bigger number? You get a smaller fraction. If you get a smaller fraction, that's going to mean a smaller density. A lower density means something's going to float. Water has a density of 1 gram per milliliter. Ethanol has a density of 0.7 grams per milliliter. If ethanol didn't dissolve, what would happen? It would float on top of the water. Many organic compounds have a density below 1, and so they float. Anything with a density above 1 would then sink. So hot air has a density that is smaller than cold air. So hot air rises, cold air then sinks. So that has to do with our weather. But okay. So what is the density of 1 mole of xenon gas at standard temperature and pressure? We can, in this case, I'm saying, what is density given the identity of the gas? So how do you know this equation from the last one? You'll have things like density or molar mass mentioned. It will actually measure, say, density. So we have density equals pressure times molar mass divided by RT. Now this one really looks like, We're not given enough information. But you got to remember standard temperature and pressure. Standard temperature and pressure. STP is 273 Kelvin and 1 ATM. So we know our pressure. We know our temperature. R has to relate to them, so we're going to use the 8206 one. The only thing we need to know is what is the molar mass of xenon. In that case, we would look that up on the periodic table. If I remember right from yesterday, it was 131.3 grams per mole. So plugging this in, I'm going to do this in long ways so that we can see all the units and see what happens. TM, 131.3 grams per mole. We have 1 over 273 Kelvin and 0.08206 atmosphere liters mole Kelvin. So what starts happening? Ooh, shoot. What starts happening? I plug in all of our values. 1 atmosphere times 131 divided by 273 divided by R. Our atmospheres cancel out. Our moles cancel out. Our Kelvin cancel out. So the units we're going to have left is grams and liters. Grams and liters. So we do this math. 131 3 divided by 273 divided by our R. What do we get? 5.86. Ooh, that feels dense. 5.86. That feels dense. But the units, grams per liters. Grams per liters. Remember, water is 1 gram per milliliter. Milliliter. So even though this is a big number, this number is still lighter than water. If I spilled some xenon in here, it would sink to the floor, but it would float over water. You may have seen this if you've watched some of the older Mythbusters. They would pour a heavy gas like xenon or argon into a fish tank, and then they would float a boat on it because the heaviness of this gas would keep it from floating out of the fish tank. But the fact that if you can make the boat light enough, it will float on the barrier between the two gases. It will be lighter than, say, argon or xenon, but heavier than the air, which is going to keep it from floating away, but it's going to keep it floating on top of the gas. So all that comes from the basic idea of if we know the gas, we can figure out the density. We know the gas, we can figure out the density. Alternatively, I could give you a density and you could figure out what is the molar mass of this gas. And so we can do just that. Now, I'm going to check the next slide, but if I'm not mistaken, this is where we're going to stop for today. Yes, we're finishing a little early, but I want to keep both classes on the same page.